Welcome. You have found your way to this quiet space at the end of the day. As you settle in, let the concerns of your hours fade. Tonight we are going to explore something simple and old, how a structure made of stacked trees kept people warm through the coldest nights of winter. For thousands of years, in the forests of Scandinavia, Russia, and North America, families lived through winters where temperatures dropped far below freezing. Darkness came early and stayed late. The cold was not an inconvenience. It was a condition that shaped every decision, every action. In this environment, the log cabin was not just shelter. It was a system for holding warmth through the long hours between sunset and dawn. These structures used no complex technology. They relied on the properties of wood, the careful sealing of gaps, and the patient management of fire. There was no single element that made them work. It was the combination. Thick walls that stored heat, joints sealed with earth and moss, small rooms that concentrated warmth, fires banked with ash to last through the night. Each part supported the others. Tonight, we will move through this system slowly. We will see how heat moved through solid wood, how gaps were sealed against the wind, how a single fire could warm a room for 12 hours without being tended. We will follow the rhythm of a winter night, from the banking of the fire at dusk to the rekindling at dawn. So settle in. Let the story unfold at its own pace. This is how people stayed warm when winter lasted half the year. The fire burns hot in the afternoon. By evening, it's been reduced to a pile of glowing coals, covered with a layer of fine ash. The family goes to bed. Outside, the temperature drops to 20 below zero. Inside, the room stays warm enough for sleep. No one tends the fire through the night. No fuel is added. And yet, when morning comes, the room has not frozen. This is the central puzzle of the log cabin. A single burn. Carefully managed provides heat that lasts 12 hours or more. The fire itself may be reduced to barely glowing embers, but the warmth persists. The answer lies not in the fire alone, but in what surrounds it. The walls of a log cabin are not like the walls of a modern home. They are not thin barriers backed by insulation. They are solid wood, 8 to 10 inches thick, stacked horizontally and sealed at the joints. These walls do more than block the wind. They absorb heat during the hours when the fire burns high, and they release that heat gradually through the night. The process is slow, steady, and remarkably efficient. This phenomenon is called thermal mass. It describes the ability of a material to store energy in the form of heat and release it over time. A log wall, because it is dense and thick, acts as a kind of battery. While the fire burns, the surface of the logs facing the interior absorbs radiant heat. That energy does not pass immediately through the wood to the cold exterior. Instead, it migrates inward, deeper into the log, where it is held. The thicker the log, the more heat it can store. But thickness alone is not enough. The type of wood matters. The way the logs are joined matters. The seals between them matter. Every part of the structure contributes to the system. If the joints leak air, the stored heat escapes. If the wood is too dense, it conducts heat away too quickly. If the room is too large, the fire cannot charge the walls fully before nightfall. The log cabin, in its most successful form, is a structure where every element has been optimized not through calculation, but through generations of lived experience. Builders learned which trees to cut, how to shape them, where to place the hearth, how high to build the ceiling. They learned by surviving winters, by noting what worked and what failed. The knowledge was practical, immediate, and life-preserving. In the coldest regions of the world, this knowledge was the difference between endurance and abandonment. A poorly built cabin meant waking to frost on the inside walls, meant burning through a winter's supply of firewood in half the time, meant children too cold to sleep. A well-built cabin meant warmth through the night, meant wood supplies that lasted, meant the possibility of making it to spring. The question of lasting warmth, then, is a question about system design. It's about how heat moves through materials, how air moves through gaps, how human behavior adapts to the limitations of fire and fuel. The fire provides the energy. but it is the cabin itself, the walls, the ceiling, the floor, the carefully managed openings that determines whether that energy is wasted or preserved. We start with the simplest part of the system, the material itself. Before we can understand how a cabin holds heat, we need to understand what logs are made of and why wood, of all materials, became the foundation for shelter in the coldest places on Earth. The boreal forest stretches across the northern latitudes in an unbroken band. It covers Scandinavia, Russia, Canada, and parts of the northern United States. It is one of the largest terrestrial biomes on the planet, and for thousands of years, it has been the primary source of building material for people living in extreme cold. The trees that grow here are different from those in temperate or tropical regions. They are conifers, pines, spruces, firs, and cedars, species adapted to short growing seasons and long frozen winters. These trees grow slowly. Their wood is softer than that of hardwoods, like oak or maple, and it can be worked with simple hand tools. An axe and an adze are enough to fell a tree, strip its bark, and shape it into a building component. This accessibility mattered. In regions where metal was scarce and nails were expensive, construction methods had to rely on the material properties of the wood itself. Logs could be stacked horizontally and locked together with notched corners. No fasteners were needed. The weight of the structure held it in place. This method required trees that were straight, uniform, and available in large numbers. The boreal forest provided all three. But accessibility alone does not explain why log construction became the dominant form of shelter in these regions. The deeper reason has to do with the way wood interacts with heat. Wood is not a solid, homogeneous material. It is composed of millions of tiny cells, most of which are hollow. These cells once transported water and nutrients through the living tree. After the tree is cut and the wood is dried, the cells remain, filled with air. Air is one of the best insulators available. It does not conduct heat well. When air is trapped in small pockets, as it is inside the cells of wood, it resists the transfer of thermal energy. This makes wood, particularly softwood, an effective insulating material. A thick log wall, made of timber with a high proportion of air-filled cells, provides a natural barrier against the cold. Not all wood performs equally in this regard. Denser woods like oak or hickory contain more solid material and fewer air pockets. They are stronger, but they also conduct heat more readily. Softwoods like pine and cedar are less dense. Their cell walls are thinner, and the spaces between cells are larger. This gives them a higher insulating value per inch of thickness. Among the softwoods, certain species stand out. Northern white cedar, for example, has a cellular structure that resists moisture absorption. Its cells are closed and tightly packed, which prevents water from entering the wood and causing rot or swelling. This stability is critical in a climate where freeze-thaw cycles can damage materials that absorb and release moisture repeatedly. Cedar logs remain dimensionally stable over decades, and they do not develop the deep cracks, called checks, that allow cold air to bypass the wood's insulation. Eastern white pine was another common choice. It is lighter than cedar and easier to work, and it provides good insulation. However, pine is more prone to checking as it dries. Builders who used pine often preferred logs that had been air-dried or seasoned for a year or more before construction. This allowed the wood to reach a stable moisture content, reducing the likelihood of cracks forming after the cabin was built. The process of selecting and preparing timber was not casual. Trees had to be felled in winter when the sap was down and the wood contained less moisture. Logs cut in summer would weep resin and take much longer to dry. Winter-cut logs could be stacked and allowed to season through the following months, losing moisture gradually without warping or splitting excessively. The forest, then, was not just a source of raw material. It was a system that provided the right material at the right time, if the builder understood the rhythms of growth, harvest, and drying. The trees that survived in the boreal climate had evolved to withstand cold, and their wood carried properties that made them ideal for creating warmth in structures exposed to that same cold. This was a match between environment and material. The forests of the north gave wood that could be shaped easily, stacked efficiently, and relied upon to resist heat loss. The cabins built from these trees were not impositions on the landscape. They were extensions of it, using what the land provided in a way that answered the land's harshest question: how do you survive winter? The answer began with the tree. But the tree, once cut and shaped, had to be understood not just as a structural element, but as a thermal one. The next step was to recognize that the walls of a cabin were not just barriers, they were reservoirs. A log, when examined closely, reveals a structure that seems designed for the task of holding warmth. Under magnification, the wood surface dissolves into a landscape of channels and chambers. These are the cells that once carried water from the roots to the leaves. In a living tree, they form a transportation network. In dried lumber, they form something else, a matrix of trapped air. Each cell is a hollow tube with walls made of cellulose and lignin. The walls are thin, and the interior space is large relative to the wall thickness. When the tree is cut and the moisture evaporates, these tubes fill with air. The air does not move. It is locked in place by the structure of the wood. And because air conducts heat poorly, each cell becomes a tiny insulating pocket. This is why wood feels warm to the touch, even in a cold room. Metal conducts heat away from your hand quickly, making it feel cold. Wood does not. The air trapped in its cells resists that transfer. Your hand stays warm, and the wood feels neutral, even pleasant. This same property makes wood an effective material for the walls of a shelter. The insulating value of wood is measured in R value, a number that describes resistance to heat flow. The higher the R value, the better the insulation. Northern white cedar has an R value of approximately 1.41 per inch of thickness. An 8-inch log, then, provides an R value of around 11. For comparison, modern fiberglass insulation typically has an R value of 3 to 4 per inch. The log does not match fiberglass inch for inch, but it does not need to. The log performs a second function that fiberglass cannot. It stores heat. This storage capacity is what separates a log wall from a conventional insulated wall. Fiberglass, foam, and other modern insulators are designed to resist heat flow, but they do not hold heat. A fiberglass insulated wall in a house heated by forced air will warm up quickly when the furnace runs, but it will also cool quickly when the furnace stops. The wall does not retain energy. It simply slows its passage. A log wall, by contrast, absorbs heat. During the hours when a fire burns in the hearth, radiant energy strikes the interior surface of the logs. Some of that energy reflects back into the room, but much of it is absorbed into the wood. The temperature of the log surface rises. As the surface warms, heat begins to migrate deeper into the log, moving from the hot interior face toward the cooler exterior face. This migration is slow. Wood has low thermal conductivity, meaning it does not transfer heat quickly. The thicker the log, the longer it takes for heat to move from one side to the other. In an 8-inch log, this process can take several hours. By the time the heat reaches the exterior surface, the fire may have already been banked for the night. The heat that was absorbed in the afternoon does not escape until the early morning hours, and by then, a new fire is being kindled. This delay is called thermal lag. It is the reason a log cabin does not experience the rapid temperature swings common in lighter structures. In a modern home with thin walls and minimal thermal mass, the indoor temperature can drop several degrees within an hour of the heating system shutting off. In a log cabin, the temperature drops much more slowly. The walls continue to radiate stored heat long after the fire has stopped burning actively. The thickness of the log determines the duration of this effect. For typical day-night temperature cycles, the effective depth of thermal mass is about 3 to 6 inches. This is the portion of the wall that actively absorbs and releases heat over a 24-hour period. A log thicker than 6 inches does not contribute much to the daily cycle, but it does provide a buffer for multi-day cold snaps. If a fire goes out or if the weather turns severe for several days, the deeper portions of the log still hold residual warmth from previous burns. This reserve can be the difference between a habitable space and one that becomes dangerously cold. Not all wood performs this function equally well. The effectiveness of a log as a thermal battery depends on its density, moisture content, and species. Denser woods hold more heat per unit volume because they contain more mass. However, they also conduct heat more quickly, which shortens the thermal lag. Softwoods like cedar and pine strike a balance. They are dense enough to store a useful amount of heat, but light enough to delay its release. Moisture content also plays a role. Green wood, wood that has not been dried, contains significant amounts of water within its cells. Water is a much better conductor of heat than air. A wall made of green logs will lose heat more quickly than a wall made of seasoned logs. Additionally, as green logs dry in place, they shrink. This shrinkage can open gaps between the logs, creating pathways for cold air to enter. For this reason, builders preferred logs that had been dried to a moisture content of around 15% before construction. The cellular structure of wood, then, is not incidental. It is the foundation of the log cabin's thermal performance. The air-filled cells provide insulation. The solid cell walls provide mass. Together, they create a material that resists heat loss while storing heat for gradual release. This dual function is rare in building materials and central to understanding how a simple stack of logs could keep people alive through the coldest nights of the year. But the logs alone were not enough. Even the best wood, cut from the best trees, required careful assembly and sealing. The wall was only as warm as its weakest point, and in every log cabin, the weakest points were the horizontal joints where one log met the next. The first log structures appeared in the forests of northern and eastern Europe during the Bronze Age, around 3500 BC. These were not the refined cabins that would later emerge in North America. They were rough shelters built from round logs laid horizontally and notched at the corners to prevent rolling. The spaces between the logs were wide and irregular, filled with whatever material was available: moss, mud, or grass. These early buildings served multiple functions. Some were dwellings, others were smokehouses or storage sheds. The Scandinavian purty, for example, was a small gabled structure with a central hearth and no chimney. Smoke filled the interior, rising slowly through gaps in the roof. This smoke served as both a heat source and a preservative, coating the wood and food stored inside with a layer of creosote that resisted rot and insects. The lack of a chimney was not an oversight. In a climate where every unit of heat mattered, venting smoke directly outside would have wasted energy. By allowing the smoke to linger, the structure retained more warmth. The inhabitants adapted to the discomfort, and over time, the smoke-filled interior became a defining feature of the northern dwelling. Eyes watered, throats grew accustomed to the sting. But the room stayed warm, and the wood stayed preserved. Over the next several thousand years, log construction techniques spread and evolved. By the medieval period, builders in Scandinavia and Russia had developed more sophisticated corner joints. The simple notch was replaced by interlocking systems that provided greater structural stability and reduced the size of the gaps between logs. These joints required more skill and better tools, but they created walls that were tighter and more durable. The dovetail joint, for example, allowed the ends of the logs to interlock in a way that resisted both vertical and horizontal movement. The saddle notch, another common technique, involved cutting a rounded groove in the top of one log to match the curvature of the log below. These joints did more than hold the structure together. They minimized the gaps where cold air could infiltrate. In the 17th century, these techniques crossed the Atlantic. Swedish and Finnish settlers arriving in the region that would become Delaware brought with them the knowledge of log construction. They built the first log cabins in North America using the same interlocking corner joints that had been refined in Scandinavia over millennia. The local forest provided an abundance of suitable timber, and the method required no nails or complex tools. Within a generation, other immigrant groups, Scots, Irish, Germans, English, had adopted the technique. The log cabin became a defining feature of the American frontier. It was practical, durable, and could be built by a small group of people in a matter of days. But more than that, it was adaptable. Builders modified the basic design to suit local climates and available materials. In the Appalachian Mountains, cabins were often built with a single room and a loft, heated by a stone fireplace at one end. In the Great Lakes region, cabins were sometimes built with double walls, an inner and outer layer of logs with an air gap between them for added insulation. One of the most significant refinements was the transition from round logs to hewn logs. Round log, even when carefully selected, has an irregular surface. The gaps between stacked round logs are wide and difficult to seal. Hewing, shaping the log with an axe or adze to create flat surfaces on 2 or 4 sides, allowed for much tighter joints. The flat sides of the logs nested together with minimal gaps, reducing the amount of chinking required and improving the overall airtightness of the wall. This process was labor-intensive. Hewing a log required skill and time. Each face had to be cut to a consistent thickness, and the wood had to be worked carefully to avoid splitting. But the effort was justified by the result. A cabin built from hewn logs was warmer, sturdier, and more permanent than one built from round logs. It was a sign that the builder intended to stay, to invest in the land, and to endure the winters ahead. By the 19th century, log construction had reached a high level of refinement. Cabins were no longer seen as temporary shelters, but as lasting homes. The techniques varied by region, but the underlying principles remained the same. Use the best available wood, join the logs tightly, seal the gaps, and design the interior space to maximize the efficiency of the hearth. These principles were not written down in manuals. They were passed from builder to builder, learned through observation and apprenticeship, and proven through the survival of families in conditions that offered little margin for error. The lineage of the log cabin, then, is a lineage of adaptation. From the smokehouse of Bronze Age Scandinavia to the frontier homestead of 19th century America, the basic structure evolved in response to climate, materials, and need. Each generation of builders refined the techniques they inherited, making walls tighter, joints stronger, and interiors warmer. The result was not a single design, but a family of designs, all sharing a common logic that stacked logs, properly joined and sealed, could provide warmth in places where warmth was not guaranteed. But the joining of the logs was only the beginning. The real challenge lay in sealing the inevitable gaps and in understanding that the seal itself had to be as dynamic as the wood it protected. A round log, as it comes from the forest, is rarely uniform. Trees grow in response to wind, slope, and competition for light. They taper from base to crown. They develop bends and irregularities. When stacked horizontally, these natural variations create gaps. Some narrow, some wide, all of them potential pathways for cold air. The earliest log builders accepted these gaps as unavoidable and filled them with whatever material was at hand. Mud, grass, and moss were common. These fillers provided some insulation, but they were not permanent. Mud cracked as it dried. Grass decayed. Moss compressed and had to be replaced regularly. The seal was always provisional, requiring maintenance each season. The decision to hew logs, to shape them with axes and adzes into squared or flat-sided timbers, was a response to this problem. Hewing allowed the builder to create surfaces that met with far greater precision. A log hewn flat on 2 sides could be stacked so that the flat surfaces faced each other, reducing the gap between courses to a fraction of an inch in some places. The remaining gaps were smaller, more uniform, and easier to seal permanently. This transition from round to square was not merely aesthetic, it was functional. A cabin built from hewn logs required less chinking material, and the chinking that was used could be applied more effectively. The reduced gap size meant that the seal was less likely to fail under the stress of seasonal expansion and contraction. And because the flat surfaces of the logs provided more contact area, the structure itself was more stable. The logs did not roll or shift. They locked together through sheer surface friction and the weight of the courses above. Hewing was hard work. It required strength, skill, and time. A single log, depending on its size, could take several hours to hew on 2 sides, and longer if all 4 sides were to be dressed. The process began with felling the tree and removing the branches. The log was then elevated on supports. Often 2 other logs laid parallel, so that it could be worked from the side without striking the ground. The hewer would start by scoring the log. Using an axe, he would make a series of cuts perpendicular to the length of the log, each cut going about halfway through the diameter. These score marks created weak points. The wood between the cuts could then be split away with a broad axe or removed with an adze, leaving a relatively flat surface. The final step was to smooth the surface with a draw knife or plane, though on many frontier cabins, this finishing step was skipped. The rough-hewn surface was good enough. The effort required to hew logs meant that not all cabins were built this way. In temporary camps or in situations where speed was essential, round logs were used, but for permanent dwellings, homes meant to last a generation or more, hewing was standard practice. It was a marker of commitment. A man who took the time to hew his logs was a man who intended to stay through the winter, and the winter after that. The impact on warmth was immediate and measurable. A cabin built from hewn logs was noticeably warmer than one built from round logs of the same species and thickness. The improved seal meant that less heat was lost to air infiltration, and the thermal mass of the walls could function as intended. The fire's energy stayed inside, stored in the wood, rather than leaking out through gaps in the chinking. But even hewn logs were not perfect. Wood is not a static material. It absorbs and releases moisture in response to changes in humidity. It expands in damp conditions and contracts in dry ones. In the freeze-thaw cycles of a northern winter, this movement can be significant. A log that fits tightly in autumn may shrink in the dry cold of January, opening a crack along the joint. A log that fits well in winter may swell in the damp air of spring, compressing the chinking until it bulges or cracks. Builders understood this movement. They did not try to prevent it. Instead, they designed the seal to accommodate it. The chinking and daubing system, which filled the gaps between the logs, was not rigid. It was layered, flexible, and designed to move with the wood. This system was as important to the cabin's thermal performance as the logs themselves, and it required knowledge of materials, weather, and time. The next step, then, is to understand how those gaps were sealed, not once, but continuously, through materials that could breathe, compress, and endure the same cycles of expansion and contraction that the logs themselves experienced. The seal was not a boundary. It was a relationship between wood, earth, and the changing seasons. The horizontal seam between two stacked logs is where the integrity of warmth is tested. No matter how carefully the logs are selected, no matter how skillfully they are hewn, the joint remains a line of weakness. Wood is irregular. Even flat surfaces have subtle variations, and wood moves. It swells with moisture. It shrinks as it dries. A joint that is tight in October may open by half an inch in February. Cold air seeks these openings. It moves through the smallest gaps, driven by the difference in pressure between the warm interior and the cold exterior. In a log cabin, the joints between courses are the primary pathway for infiltration. A single poorly sealed joint can allow enough cold air into a room to drop the temperature by several degrees, forcing the fire to burn hotter and longer to compensate. Over the course of a winter, this means the difference between a cord of wood and two cords, between comfort and constant cold. The vulnerability is not evenly distributed. The greatest risk occurs at the ends of the logs, where they meet at the corners. Here, the wood is cut or notched, exposing end grain. End grain absorbs and releases moisture much more readily than the sides of the log. It swells and shrinks more dramatically. And because the corners are the most exposed part of the structure, open to wind from two directions, they are the first places where gaps appear. Builders recognize this. The corner joint was often the most carefully executed part of the cabin. A well-cut dovetail or saddle notch could lock the logs together so tightly that the joint itself provided much of the seal. But even the best corner joint could not eliminate the gap entirely. Some space always remained, and that space had to be filled. The second area of vulnerability was along the length of the joint, particularly in sections where the natural taper of the log created a wider gap. A tree is thicker at the base than at the crown. When logs were laid alternately, butt end one way, crown end the other, the taper was somewhat equalized, but variations in diameter still created irregular gaps. In some places, the logs touched. In others, there was a gap of an inch or more. These gaps were not just thermal problems. They were also structural concerns. An unsealed gap allowed the log above to sag or shift. Over time, this could lead to misalignment of the entire wall. The logs could twist. The corners could pull apart. The roof could settle unevenly. Sealing the joint, then, was not only about warmth. It was about the long-term stability of the building. Water infiltration was another risk. Rain and melting snow could enter through the gaps, soaking the wood and promoting rot. In the freeze-thaw cycles of spring and autumn, water trapped in the joint could freeze, expanding and forcing the gap wider. This process could damage both the logs and the chinking material. A cabin that was not properly sealed could begin to deteriorate within a few years, the logs softening and the walls losing their structural integrity. The traditional response to this vulnerability was a two-part sealing system. The first part was the chinking, a rigid or semi-rigid material that filled the bulk of the gap and provided structural support. The second part was the daubing, a flexible, weatherproof coating that sealed the chinking and protected it from the elements. Together, these materials created a joint that could move with the wood, resist water, and block the flow of air. This system was not applied once and forgotten. It required maintenance. The daubing cracked over time, especially on the south-facing walls, where sun exposure caused rapid drying. The chinking settled or was dislodged by the movement of the logs. Each autumn, before the first snow, the cabin had to be inspected. Cracks were filled. Loose chinking was replaced. Daubing was reapplied. This annual ritual was as essential as stacking firewood or repairing the roof. Without it, the cabin could not hold warmth through the winter. The vulnerability of the joint, then, was not a flaw in the design. It was a known challenge, addressed through careful material selection and ongoing care. The seal between the logs was never permanent in the sense of being unchanging. It was permanent in the sense of being maintainable, adaptable, and sufficient to the task. The joint moved, the seal moved with it, and as long as the builder understood this relationship, the cabin remained warm. The next question is what materials made this possible? What could be packed into a gap between two logs that would compress without crumbling, insulate without rotting, and endure the expansion and contraction of the wood through dozens of freeze-thaw cycles? The answer was found in the forest, the field, and the lime kiln. The process of sealing a log cabin began with the chinking. This was the material that filled the majority of the gap between logs, providing bulk and structure. In its simplest form, chinking was nothing more than stones or wood chips driven into the space until it was tightly packed. In more refined applications, it involved carefully shaped blocks of wood, split shingles, or even small logs fitted to the contour of the gap. The purpose of the chinking was to create a stable base for the daubing. It had to be rigid enough not to fall out under its own weight, but it also had to fit the irregular shape of the gap. In places where the space was wide, larger stones or wood blocks were used. In places where it was narrow, smaller materials were wedged in tightly. The goal was to leave as little empty space as possible so that the daubing would have a solid backing and would not sag or collapse inward. Woodblock chinking was common in the Appalachian region. Builders would split small sections of log into wedge shapes and drive them into the gaps with a mallet. The wedges compressed slightly as they were driven in, creating friction that held them in place. This method was fast and used material that was readily available, often scraps left over from hewing or splitting firewood. The wood itself provided some insulation, and because it was dry and tightly fitted, it resisted rot better than organic fillers like grass or straw. In regions where suitable stone was available, rock chinking was preferred. Flat stones could be stacked within the gap, creating a stable wall that extended from one log to the other. The stones did not compress, which meant they provided a permanent structural support for the daubing. However, stone conducted heat more readily than wood, so care had to be taken to ensure that the stones did not create a thermal bridge, a pathway through which heat could escape directly from the interior to the exterior. Once the rigid chinking was in place, the next step was to pack the remaining voids with a soft, compressible material. This was the insulating layer. It had to fill the smallest crevices and conform to the irregularities of the wood. It had to be dry enough not to promote rot, but flexible enough to compress and expand with the movement of the logs. Sphagnum moss was the traditional choice in Scandinavia and parts of Canada. This moss grows in wetlands and has natural antibacterial properties. When dried, it becomes springy and compressible. It can be packed tightly into a narrow gap, and it will retain its shape while still allowing for some movement. Importantly, it resists decay. Cabins chinked with sphagnum moss in the 19th century have been found with the original moss still intact, dry and functional after more than 100 years. In regions where sphagnum was not available, other materials were used. Oakum, jute fibers soaked in pine tar, was common in maritime regions and later became a standard material in North America. The tar acted as a preservative and a water repellent, while the fibers provided bulk and insulation. Oakum was also used in shipbuilding to seal the gaps between planks, and its effectiveness in that context translated well to log construction. Straw, animal hair, and strips of cloth were also used, particularly by settlers who lacked access to moss or oakum. These materials were less durable. Straw could rot if it became wet. Cloth could compress over time and lose its insulating value, but in the short term, they were effective, and they could be replaced as needed. The key was to ensure that the material was dry when it was installed, and that it was packed densely enough to resist being pulled out by wind or animals. The final layer was the daubing. This was the weatherproof seal that covered the chinking and the soft filler, protecting them from rain, snow, and wind. Daubing was typically a mixture of clay, sand, and lime, with various binders added to improve adhesion and flexibility. The exact recipe varied by region and availability of materials, but the principles were consistent. Clay provided the bulk and plasticity. It could be molded to fill gaps, and could be smoothed to create a finished surface. Sand added strength and reduced cracking as the mixture dried. Lime was the critical component. Lime-based mortars are breathable, meaning they allow water vapor to pass through. This is essential in a log cabin, where the logs themselves need to release moisture as they dry and contract. A non-breathable seal, such as cement, would trap moisture against the wood, leading to rot. Lime also has mild antimicrobial properties, which help prevent mold and fungus growth at the joint. And lime mortar remains somewhat flexible even after it cures, which allows it to move with the logs rather than cracking and falling away. The traditional ratio is 1 part lime to 4 parts sand, though this could be adjusted based on the quality of the lime and the specific conditions of the site. Binders were added to give the daubing tensile strength. Hog bristles, horsehair, and straw were common. These fibers acted like rebar in concrete, preventing the daubing from cracking under stress. They also helped the mixture adhere to the wood and the chinking material. Without these binders, the daubing would dry into a brittle shell that could easily be dislodged by the movement of the logs or the impact of weather. The daubing was applied by hand. It was pressed into the gaps, covering the chinking and filler completely. The surface was smoothed with a trowel or a wet hand, and in some cases it was scored or textured to improve its grip on the wood. The process was messy and time-consuming, but it was also straightforward. A family could daub a small cabin in a day or two, working together to seal the structure before the first frost. The result was a joint that was no longer a gap, but a composite material. Wood, stone, moss, and mortar working together to resist air infiltration and water penetration. The seal was not impermeable, but it did not need to be. It needed only to be good enough to allow the thermal mass of the logs to function as intended and to prevent the cold from stealing the heat that the fire had worked so hard to provide. This sealing system was refined over centuries, but it was never standardized. Each builder adapted it to the materials at hand and the specific challenges of the site. A cabin built near a wetland might use more moss. A cabin built near a quarry might use more stone. A cabin built in a dry climate might use less lime and more clay. The system was flexible, local, and effective. And it was this flexibility that allowed the log cabin to spread across vastly different regions, from the damp forests of Scandinavia to the arid highlands of the American West. But sealing the joints was only part of the equation. The warmth of the cabin also depended on how the heat moved through the structure once it was inside, and that movement was governed by the physics of thermal mass. The materials used to seal a log cabin were not chosen arbitrarily. They were selected for properties that went beyond simple insulation. A good chinking material had to compress without disintegrating. A good filler had to resist rot. And the daubing had to allow the wall to breathe, to permit moisture to escape without allowing cold air to enter. This concept of a breathing wall is central to understanding why traditional log cabins performed well over long periods. Modern construction often prioritizes airtightness above all else, using materials like plastic vapor barriers and synthetic caulks to create a completely sealed envelope. This approach works in the context of modern heating systems and mechanical ventilation, but it would fail in a log cabin. The logs themselves are hygroscopic, meaning they absorb and release moisture in response to changes in humidity. If that moisture cannot escape, it accumulates in the wood, leading to rot, mold, and structural failure. Lime mortar, the traditional daubing material, solves this problem. It hardens through a chemical process called carbonation, in which the lime reacts with carbon dioxide in the air to form calcium carbonate. This process creates a material that is solid and durable, but also porous at a microscopic level. Water vapor can pass through lime mortar, moving from the interior of the cabin, where humidity is higher due to cooking, breathing, and the presence of people, to the exterior, where it evaporates. This permeability prevents condensation from forming within the wall. Condensation occurs when warm, moist air contacts a cold surface, and the moisture condenses into liquid water. In a wall sealed with a non-breathable material, this condensation can occur at the interface between the wood and the seal, creating conditions ideal for decay. In a wall sealed with lime mortar, the moisture moves through the mortar before it has a chance to condense, keeping the wood dry and stable. The choice of filler material also affected the wall's ability to breathe. Sphagnum moss, with its natural antibacterial properties and open structure, allowed air and moisture to move through it while still providing insulation. The moss did not pack down into a solid mass. It retained a degree of loft, creating small air pockets that resisted heat transfer while allowing vapor to escape. Oakum, though denser than moss, also permitted some degree of vapor movement. The jute fibers, even when soaked in pine tar, were not completely impermeable. The tar acted as a water repellent, preventing liquid water from entering the joint, but it did not prevent vapor diffusion. This distinction is important. Liquid water can cause immediate damage, soaking into the wood and promoting rot. Water vapor, if it can escape, poses much less of a threat. The layered approach to sealing, rigid chinking, compressible filler, breathable daubing, created a joint that could accommodate the seasonal movement of the logs without failing. In winter, when the wood was dry and contracted, the soft filler compressed to maintain contact with the logs. In summer, when the wood absorbed moisture and expanded, the filler was pushed slightly outward, but the lime mortar flexed rather than cracking. The system moved with the wood, maintaining the seal through dozens of cycles of expansion and contraction. This dynamic quality is what separated traditional sealing methods from modern ones. A bead of silicone caulk, for example, creates an airtight seal that is initially very effective. But silicone does not breathe, it does not compress, and it does not accommodate large movements. When the logs shrink in winter, the silicone can pull away from the wood, leaving a gap. When the logs expand in summer, the caulk has nowhere to go, and it can buckle or tear. The seal fails, and with it, the thermal performance of the wall. Traditional builders did not think in terms of vapor permeability or thermal bridging, but they understood the behavior of materials through observation. They knew that lime mortar lasted longer than clay alone. They knew that moss did not rot the way straw did. They knew that a wall sealed in autumn might need touch-up work in spring. This knowledge was empirical, passed down through practice, and it was sufficient to create structures that lasted for generations. The pine tar used in Oakum served an additional function beyond water repellency. It acted as an insect deterrent. Beetles and other wood-boring insects were a constant threat to log structures, particularly in warmer months. The tar's strong odor and chemical composition made the treated areas unattractive to insects, protecting the most vulnerable parts of the wall, the joints, from infestation. In some regions, builders would apply a thin layer of lime wash to the exterior daubing as a final protective coating. Lime wash is a diluted lime solution that dries to a white or off-white finish. It provides an additional barrier against rain and sun, and it has the added benefit of being reflective, which can reduce heat absorption in summer. The lime wash also needed to be reapplied periodically, typically every few years, as it weathered and washed away. This maintenance was part of the rhythm of living in a log cabin, an ongoing conversation with the structure, a recognition that the building was not a static object, but a living system that required care. The breathing wall, then, was not a metaphor. It was a functional characteristic of the construction. The wall inhaled and exhaled moisture. It moved with the seasons. it adapted to the conditions inside and outside the cabin, and in doing so, it remained dry, stable, and capable of performing its primary function, holding the heat that would be stored in the mass of the logs. That mass and the way it stored and released heat is the next part of the system to understand. The seal kept the cold out and the moisture in balance, but it was the logs themselves, the sheer thickness and density of the wood, that turned a fire's energy into lasting warmth. A log wall does not insulate in the way a modern wall does. It does not rely on layers of low-density material to trap air and resist heat flow. Instead, it uses mass. The logs are thick and heavy. They contain a large volume of solid material, and that material has the capacity to absorb energy in the form of heat. Once absorbed, that heat is released slowly over many hours, creating a stable indoor temperature that does not fluctuate with the cycles of the fire. This principle is thermal mass, and it operates according to the laws of thermodynamics. When a material absorbs heat, its temperature rises. The amount of heat required to raise the temperature of a given mass by 1 degree is called the specific heat capacity. Wood has a moderate specific heat capacity, not as high as water or stone, but higher than many other building materials. This means that a log wall can store a significant amount of energy without becoming dangerously hot to the touch. The process begins when the fire is lit. Radiant heat from the flames and coals strikes the interior surface of the logs. Some of this energy is reflected back into the room, warming the air, but much of it is absorbed into the wood. The surface of the log heats up. As it does, the temperature gradient between the interior surface and the deeper portions of the log increases. Heat begins to move inward, conducted from the hot surface toward the cooler core. This conduction happens slowly. Wood is a poor conductor of heat, particularly across the grain. The cellular structure that makes wood a good insulator also makes it slow to transfer heat through its thickness. In an 8-inch log, it can take 4 to 6 hours for heat to migrate from the interior surface to the exterior surface. This delay is the thermal lag, and it is the key to understanding how a cabin stays warm overnight. During the afternoon and early evening, when the fire burns steadily, the logs continue to absorb heat. The temperature of the wall's interior surface may reach 90 or 100 degrees Fahrenheit, well above the ambient room temperature. The heat moves deeper into the log, warming the wood several inches into the wall. By the time the fire is banked at sunset, the logs have stored a substantial amount of energy, enough to continue radiating warmth into the room for many hours. As the night progresses and the fire dies down to smoldering coals, the room begins to cool. But it cools slowly. The logs, which are now warmer than the air, begin to release their stored heat. The interior surface of the wall radiates energy back into the room, warming the air and any objects, bedding, furniture, people, that are nearby. This radiant heat is gentle and even. It does not create the sharp temperature spikes of a roaring fire, but it maintains a baseline warmth that prevents the room from becoming dangerously cold. The exterior surface of the log also radiates heat, but this heat is lost to the cold, outside air. However, because the exterior surface is the last part of the log to warm up, it is also the last part to cool down. By the time the exterior begins to lose significant heat, the interior has already started to warm again with the morning fire. The log, in effect, is always playing catch-up with the temperature changes, and this delay smooths out the extremes. The thickness of the log determines how long this buffering effect lasts. A thin wall, say 4 inches, will charge and discharge quickly. It can provide some thermal mass effect over a few hours, but it will not carry through a full night. An 8 to 10-inch wall, by contrast, has enough depth to absorb heat throughout the day and release it through the night. The effective depth for a 24-hour cycle is about 6 inches. Beyond that, the heat does not penetrate significantly in a single day. But that deeper reserve still matters during multi-day cold snaps, when the fire may burn continuously for days and the entire wall reaches a higher equilibrium temperature. Research conducted by the National Bureau of Standards in the early 1980s confirmed what traditional builders had known intuitively. In controlled tests, log buildings performed as well as conventionally insulated frame buildings with R values 20% higher. In spring and autumn, when outdoor temperatures fluctuated more widely, the log buildings used up to 46% less energy. The thermal mass was buffering the temperature swings, reducing the need for supplemental heating. This effect is most pronounced in climates with large diurnal temperature swings, places where the days are warm and the nights are cold. In such conditions, the logs absorb heat from the sun and the fire during the day and release it at night, creating a passive heating system that requires no external input once the fire is established. In the deep cold of a northern winter, where temperatures remain below freezing day and night, the effect is less dramatic, but it is still significant. The logs prevent the sharp drops in temperature that would occur in a less massive structure. The type of wood also influences the thermal mass effect. Denser woods like oak or maple have more mass per unit volume and can therefore store more heat, but they also conduct heat more quickly, which shortens the time lag. Soft woods like pine and cedar have less mass, but they retain heat longer because their lower density slows conduction. The ideal wood for a log cabin, then, is one that balances mass and conductivity, dense enough to store useful amounts of heat, but light enough to delay its release. The moisture content of the wood also plays a role. Dry wood stores heat more effectively than wet wood because the air in the cells acts as an insulator. Wet wood with water in the cells conducts heat more readily and stores it less efficiently. This is one reason why seasoned logs were preferred. They performed better thermally, and they did not shrink and crack as much after the cabin was built. Thermal mass, then, is not a passive resistance to cold. It is an active storage and release system, a way of capturing energy when it is abundant and redistributing it when it is scarce. The fire provides the energy, but it is the logs that make the energy useful over time. Without the mass of the walls, the fire would heat the room quickly, but the heat would dissipate just as quickly. With the mass, the heat lingers, creating a stable environment that does not require constant tending. This storage capacity is what allowed pioneers to sleep through the night without freezing, and it is what made the log cabin a viable form of shelter in climates where other building methods would have failed. But the mass alone was not enough. The cabin's warmth also depended on how the interior space was designed, on the size of the rooms, the height of the ceilings, and the placement of the fire. The movement of heat through a log wall is not instantaneous. It is a process measured in hours governed by the material properties of wood and the laws of heat transfer. This delay, this thermal lag, is what transforms a log cabin from a simple shelter into a thermal battery, capable of storing the energy of a fire and releasing it gradually through the coldest hours of the night. Consider a fire lit at 2 in the afternoon. By 3 o'clock, the interior surface of the logs facing the hearth has warmed significantly. The radiant heat from the flames strikes the wood, and the surface temperature rises to 80 or 90 degrees Fahrenheit. At this point, the heat has penetrated perhaps half an inch into the log. The outer layers of cells have warmed, but the deeper wood remains at the ambient temperature of the room, which might be 60 or 65 degrees. By 4 o'clock, the heat has moved deeper. The temperature gradient within the log is now steeper. The surface is hot, the core is cool, and the heat is migrating inward along that gradient, moving from cell to cell through the solid wood fibers. This migration is slow because wood is a poor conductor. The air trapped in the cells resists the transfer of energy. The cellulose and lignin that form the cell walls do conduct heat, but not efficiently. By 6 o'clock, the fire is still burning, and the heat has penetrated 2 or 3 inches into the log. The surface temperature may have risen a bit more, but the rate of absorption has slowed. The deeper wood is now warm enough that the temperature difference between the surface and the core is less extreme. Heat still flows inward, but not as rapidly as it did in the first hours. By 8 o'clock, the fire is banked. The embers are covered with ash, and the flames have died down. The room begins to cool, but the logs do not. They are still absorbing the residual heat from the coals, and they are still radiating heat back into the room from their warm interior surfaces. The heat that entered the log at 2 o'clock is now 4 or 5 inches deep, still migrating toward the exterior surface. By 10 o'clock, the room temperature has dropped a few degrees, but it has not plummeted. The logs are now the primary heat source. Their interior surfaces, still warm, are radiating energy back into the air. This radiant heat warms the furniture, the floor, the bedding, and the people in the room. It is a gentle heat, not the intense blast of an open fire, but it is enough to keep the space comfortable. By midnight, the heat that was absorbed in the early afternoon has reached the midpoint of the log. It is now beginning to approach the exterior surface, but it still has not escaped into the cold outside air. The exterior surface of the log, exposed to freezing temperatures, is much cooler than the interior. But the cold has not yet penetrated deeply into the wood. There is a buffer zone, a region of moderate temperature, that insulates the interior from the exterior. By 2 in the morning, the heat is nearing the exterior surface. The outside of the log begins to warm slightly, radiating energy into the cold night. This is heat loss, but it is slow heat loss. The energy that left the fire at 2 in the afternoon is only now escaping into the environment, and by the time it does, the night is half over. By 4 in the morning, the coldest part of the night, the logs are still radiating warmth into the room. The energy they stored hours ago is still being released. The room temperature has dropped further, but it has not reached the point where frost forms on the windows, or where breath becomes visible inside. The thermal mass of the walls is keeping the temperature above freezing, even though the fire has been reduced to a faint glow of embers beneath a layer of ash. By 6 in the morning, the first light of dawn appears. Someone in the household rises, moves to the hearth, and rakes the ash away from the embers. The coals, still glowing faintly, are exposed to fresh air. Kindling is added. Within minutes, the fire catches again, and the cycle begins anew. The logs, which have been discharging heat all night, now begin to absorb it again. The interior surfaces warm. The heat starts its slow journey inward, and the cabin, which has remained livable through the night, begins to warm toward the comfort of full daylight. This 8-hour delay is not a design flaw. It is the fundamental mechanism by which a log cabin provides warmth without constant tending. The fire does not need to burn hot all night because the walls have stored enough energy to compensate for the hours when the fire is low. The delay ensures that the heat produced during the day is available during the night, when it is most needed. The length of the delay depends on the thickness of the log and the temperature difference between the interior and exterior. Thicker logs have longer delays. Larger temperature differences drive heat through the wood more quickly. In the deep cold of midwinter, when the exterior temperature is 30 or 40 degrees below zero, the delay may be slightly shorter because the gradient is steeper. But even in extreme cold, an 8 to 10-inch log provides enough lag to carry the warmth through the night. This effect is most noticeable in comparison to structures without thermal mass. A tent, for example, loses heat almost immediately when the fire goes out. The fabric walls have no capacity to store energy. A modern frame house with thin walls and minimal mass also cools quickly when the heating system shuts off. The insulation slows heat loss, but it does not prevent it. There is no reservoir of stored heat to draw from. The log cabin, by contrast, is its own reservoir. The walls are the battery. The fire charges them. The night discharges them. And the cycle repeats day after day through the entire winter. This is why a cabin could keep a family alive in conditions where other shelters would have failed. The thermal mass did not eliminate the need for fire, but it reduced the demands on the fire to manageable levels. A single burn each day, carefully managed and banked at night, was sufficient. The understanding of this delay did not come from scientific study. It came from experience. Builders and inhabitants learned over time when to bank the fire for the night. They learned how much wood to burn during the day to ensure warmth through the darkness. They learned that a fire burned too hot in the evening was wasteful, because the heat would not have time to penetrate the walls before morning. And they learned that a fire allowed to die too early would leave the cabin cold by dawn. This knowledge was practical, immediate, and life-preserving. It was not written in manuals. It was taught by example, by watching, by spending a winter in a cabin, and noting what worked. The 8-hour delay was not a number. It was a feeling, a sense of how long the warmth would last, how much wood was enough, when to wake and tend the fire. But the feeling was rooted in physics, in the slow, patient movement of heat through solid wood, in the relationship between fire and mass and time. The warmth of a log cabin depended not only on the thickness of the walls and the quality of the seal, but on the volume of air that needed to be heated. A large room with high ceilings required more energy to maintain a comfortable temperature than a small room with a low ceiling. In the coldest regions, where every unit of heat mattered, the size and proportion of the interior space became as important as the construction of the walls themselves. The basic unit of the traditional log cabin was the single pen. This was a one-room structure typically measuring 16 by 18 feet, with a ceiling height of 7 feet or less. The dimensions were not arbitrary. They represented the largest space that could be effectively heated by a single hearth while still, maintaining structural integrity with available timber lengths. Logs longer than 20 feet became difficult to handle and were more likely to warp or crack as they seasoned. Shorter logs limited the size of the room, but they also made construction more manageable and reduced the weight load on the walls. The low ceiling was a deliberate choice. Heat rises through convection. Warm air, being less dense than cold air, moves upward. In a room with a high ceiling, this warm air pools in the rafters, far above the heads of the inhabitants. The space where people live and work, the lower 6 feet, remains cooler, while the unused upper volume contains most of the heat. A low ceiling prevents this stratification. The warm air has nowhere to go but across the room, creating a more uniform temperature at the level where it is actually needed. This principle was understood intuitively by builders who had spent winters in poorly designed spaces. A cabin with an 8-foot ceiling felt noticeably colder than one with a 7-foot ceiling, even if the walls and hearth were identical. The difference was the wasted volume. The extra foot of height meant an extra 100 or more cubic feet of air to heat, and that air, once heated, rose out of reach. The lower ceiling captured the warmth and held it where it could be felt. The compact dimensions of the single pen also meant that no part of the room was far from the hearth. In a 16 by 18 foot space, the farthest corner was less than 15 feet from the fire. Heat travels through air by radiation, convection, and conduction. Radiant heat from the fire could reach all parts of the room directly. Convection currents carried warm air throughout the space, and the walls, absorbing heat from the fire, radiated it back from all sides. The result was a room that heated evenly and quickly, without cold spots or drafty corners. In larger homes where multiple rooms were needed, the design often incorporated multiple pens. A saddlebag plan placed 2 pens side by side, separated by a central chimney that served both rooms. A dog trot plan separated 2 pens with an open breezeway, useful in climates where summer ventilation was as important as winter heating. Each pen remained a manageable size, heated by its own fireplace or by a shared masonry stove. The rooms were thermally independent, so that a fire in one pen did not have to heat the entire house. Rooms that were not in use could be allowed to cool, conserving fuel. The placement of the hearth within the single pen was also critical. In the coldest climates, the hearth was often located on an interior wall rather than an exterior one. This ensured that the heat radiated into the living space rather than being lost through the exterior wall. If the hearth was built against an exterior wall, as was common in milder climates, the back of the fireplace had to be well insulated, and the chimney had to be sealed carefully to prevent drafts from pulling warm air up and out of the room. In some designs, the chimney mass itself became part of the thermal system. A large masonry chimney, built of stone or brick, absorbed heat from the fire and radiated it back into the room long after the fire had died down. In Russian and Scandinavian cabins, this concept was taken to its extreme with the Pechka, a massive masonry stove that could weigh 2 tons or more. The stove was not just a heat source, it was a piece of furniture, a cooking surface, and a sleeping platform. Its sheer mass allowed it to store enormous amounts of heat, providing warmth for an entire day from a single burn. The small, well-proportioned room was also easier to seal. Fewer square feet of wall surface meant fewer joints to chink and daub. Fewer openings for doors and windows meant fewer places where drafts could enter. Every reduction in surface area and every simplification of geometry contributed to the overall efficiency of the structure. The single pen was not just warm because it was small, it was warm because its smallness reduced the number of places where warmth could be lost. This efficiency came at a cost. A single room meant no privacy. Cooking, sleeping, and living all occurred in the same space. The smoke from the fire filled the room before escaping through the chimney or roof. The smell of food, of bodies, of damp wool drying by the hearth, all mingled together. But in a climate where survival was not guaranteed, comfort was a secondary concern. The first priority was warmth. The second was the preservation of fuel. Everything else could be endured. Families adapted to the constraints of the single pen. Sleeping arrangements were efficient. Children slept in the loft where the heat rose. Parents slept on the ground floor, closer to the fire. In some cabins, the bed was placed in a corner farthest from the door, where drafts were least likely to reach. In others, the bed was built against the wall closest to the hearth so that the stored heat in the logs radiated into the sleeping area through the night. The single pen was not a permanent solution for most families. As resources allowed, rooms were added. A second pen was built, connected to the first by a shared chimney or a covered passage. A lean-to was added to the back, providing storage or additional sleeping space. But the core of the dwelling remained the original pen, the warm, compact room where the fire burned and where the family gathered during the coldest months. This room was the heart of the home, and its dimensions were determined not by aesthetics or ambition, but by the simple physics of heat and air. The size of the room then was not incidental. It was a calculated response to the limitations of fire and the properties of wood. A small room meant complete heat. A large room meant diluted heat. And in a climate where the difference between the two could mean survival or suffering, the choice was clear. But even within a small room, the warmth was not evenly distributed. Heat stratified by height. And this stratification, rather than being a problem, became a resource. The upper regions of the room where the heat concentrated were deliberately used for sleeping, creating a tiered thermal environment that maximized comfort without wasting energy. In a single-pen cabin, the vertical dimension mattered as much as the horizontal. Heat does not distribute itself evenly through a room. It rises. Warm air, lighter than cold air, moves upward through convection, accumulating in the highest available space. In a cabin with a sleeping loft, this meant that the upper level was consistently warmer than the ground floor, sometimes by 10 or 15 degrees. The loft was typically a simple platform built into the rafters, accessible by a ladder or a set of narrow stairs. It occupied the space between the ceiling beams and the underside of the roof, and it was usually low, often too low to stand upright. The loft was not a proper second story. It was a shelf, a sleeping space carved out of the air above the main room. But that shelf was the warmest place in the cabin. Children slept in the loft almost universally. In large families, 3 or 4 children might share a single mattress, their combined body heat adding to the warmth already rising from the fire below. The elderly, who felt the cold more acutely, were sometimes assigned loft spaces as well, though climbing the ladder could be difficult for those with limited mobility. The loft was warm, but it was also dark, cramped, and filled with smoke if the fire was burning actively. It was not a comfortable space by modern standards, but it was warmer than the ground floor, and warmth was the priority. The thermal advantage of the loft was not subtle. On a night when the ground floor hovered near 50 degrees, the loft might be 65. This difference was enough to allow sleep without the need for excessive bedding. A child in the loft could sleep under a single quilt and remain comfortable, while an adult on the ground floor might need 3 or 4 layers to stay warm. The loft, in effect, was a passive heat trap, capturing the energy that would otherwise have been wasted in the rafters. The construction of the loft varied. In some cabins, it was a full platform extending across the width of the room, creating a defined upper space. In others, it was little more than a few boards laid across the ceiling joists with gaps between them. These gaps allowed heat to rise through the loft and into the space beneath the roof, which helped to melt snow accumulating on the roof surface and prevented ice dams from forming. But the gaps also meant that the loft was not a fully enclosed space. It was open to the room below, and the smoke from the fire drifted upward, filling the loft before escaping through the chimney or roof vents. This smoke was a double-edged feature. It was unpleasant. It stung the eyes and coated the lungs. But it also carried heat. The hot gases rising from the fire transferred energy to the roof boards and rafters, which then radiated that heat back downward into the loft. The smoke also helped to preserve the wood, coating the timbers with a layer of creosote that resisted insects and fungal decay. Cabins that had been lived in for decades often had rafters blackened to a deep, glossy finish, each layer of soot a record of fires that had warmed the space. The temperature gradient between the ground floor and the loft was most pronounced during the hours when the fire was burning actively. As the fire died down and the room cooled overnight, the gradient decreased. The loft remained warmer, but not by as much. However, because the loft was a smaller volume of air, it retained its heat longer. The thermal mass of the roof boards, warmed by the rising smoke and hot air, radiated energy back into the loft space through the night. This created a buffer that moderated the temperature drop, even when the fire below was reduced to coals. The loft also benefited from its position within the building's thermal envelope. It was surrounded on all sides by warmer surfaces. The floor of the loft was the ceiling of the main room, and it absorbed heat from the air below. The roof above the loft, though exposed to the cold, was insulated by the loft space itself, which acted as a buffer zone between the heated interior and the frozen exterior. The walls at the ends of the loft were the upper portions of the log walls, which had absorbed heat during the day and were now radiating it back into the building. This layering of warm spaces created a thermal stratification that was highly efficient. The ground floor, though cooler, was where most of the daytime activity occurred: cooking, working, and tending the fire. The loft, warmer and quieter, was reserved for sleep. This separation allowed the fire to be banked earlier in the evening because the loft's residual warmth could sustain comfortable sleeping conditions even as the ground floor temperature dropped to levels that would have been uncomfortable for active work. In cabins without a loft, the ceiling was the underside of the roof, and the entire height of the room from floor to peak was a single volume. This meant that a significant amount of heat was lost to the upper reaches, where it served no useful purpose. The addition of a loft effectively created a second room within the same structure, and it did so without adding to the exterior surface area or the amount of wood required for construction. It was an efficient use of space and heat, and it was one reason why even the smallest cabins often included a loft if the roof pitch allowed it. The loft was not without its challenges. Access was difficult, particularly in the dark. Falls from the ladder were common, especially among children waking in the night. The low headroom meant that moving around the loft required crouching or crawling. Ventilation was poor, and the air could become stale and thick with smoke. In summer, the loft was often unbearably hot, and it was abandoned in favor of sleeping outdoors or on the ground floor with the doors and windows open. But in winter, the loft was indispensable. It was the warmest sleeping space in the cabin, and it required no additional fuel to maintain. The heat that rose naturally from the fire below was captured and held, creating a microclimate that allowed families to sleep through the coldest nights without waking to tend the fire. The loft, in this sense, was not just a structural feature. It was a thermal tool, a way of harnessing the natural behavior of heat to create comfort without waste. The next step in understanding the cabin's warmth is to look beyond the structure itself and consider the technologies that enhanced it. The open hearth, while effective, was not the only or even the most efficient way to heat a log cabin. In regions where fuel was scarce and winters were long, more advanced heating systems were developed, systems that took the principles of thermal mass and combustion efficiency to their limits. The Pechka was not a fireplace. It was a structure within a structure, a massive masonry stove that could occupy a quarter of a small cabin's floor space and weigh more than 2 tons. It was built of brick or stone, with an intricate internal labyrinth of channels and baffles designed to capture nearly all the heat from a wood fire and store it in the mass of the stove itself. Once heated, the Pechka radiated warmth for 24 hours or more, maintaining a gentle, steady temperature that required no tending and produced no open flame. The design of the Pechka was the result of centuries of refinement in the coldest inhabited regions of the world. In Russia, where winter temperatures could remain below freezing for 6 months, the efficiency of the heating system was not a matter of comfort, but of survival. Fuel was often scarce, particularly in the treeless steppes and the sparse forests of the north. A heating system that wasted wood was a heating system that could lead to death. The Pechka solved this problem by burning wood at extremely high temperatures for a short period, extracting the maximum energy from each log and then storing that energy in the masonry for gradual release. The construction of a Pechka began with a foundation. The stove was heavy, and it required a solid base that would not settle or crack under the load. In some cabins, the foundation extended below the frost line to prevent shifting. The base was typically stone or compacted earth, and it supported the weight of the stove without transferring it to the wooden floor of the cabin. Above the foundation, the firebox was built. This was a relatively small chamber designed to hold a single large load of wood. The firebox was lined with fire brick, a dense ceramic material that could withstand temperatures exceeding 2,000 degrees Fahrenheit without cracking. The size of the firebox was carefully proportioned. Too large, and the fire would not burn hot enough. Too small, and it could not hold enough wood to heat the mass of the stove fully. The key innovation of the Pechka was the baffle system. After combustion, the hot gases did not exit directly through a chimney. Instead, they were forced through a series of internal channels that wound through the body of the stove. These channels increased the contact time between the hot gases and the masonry, allowing the brick to absorb the heat before the gases escaped. In some designs, the smoke traveled up from the firebox, across the top of the stove, down through a series of vertical channels, and then back up before finally exiting through the chimney. The path could be 6 or 8 feet long compared to the straight 2-foot path of a simple fireplace. This extended path served 2 functions. First, it extracted nearly all the usable heat from the combustion gases. By the time the smoke reached the chimney, it was often cool enough to touch, indicating that the energy had been transferred to the stove. Second, it forced the combustion to occur at a very high temperature, which ensured complete burning of the wood and the volatile gases it released. A low-temperature fire produces creosote and tar, which coat the chimney and can cause dangerous chimney fires. A high-temperature fire burns these substances almost completely, leaving only fine ash and carbon dioxide. The operation of the Pechka was different from that of a continuous burn fireplace. The stove was loaded once or twice a day with a large amount of wood, sometimes as much as 50 or 60 pounds. The fire was kindled and allowed to burn at full intensity for 1 to 3 hours. During this time, the flames were bright and the roar of combustion was loud. The stove's surface became warm, but not dangerously hot. The masonry absorbed the energy, and the temperature of the stove's exterior remained at a level that could be touched without discomfort. Once the wood was fully consumed and the firebox contained only glowing coals and ash, the damper was closed. This sealed the firebox and the internal channels, trapping the heat within the masonry. The combustion stopped, and the stove entered its discharge phase. For the next 18 to 24 hours, the stove radiated heat into the room. The surface temperature remained steady, typically between 120 and 180 degrees Fahrenheit. This was warm enough to heat the room, but not so hot as to cause burns or discomfort. The heat from the Pechka was radiant rather than convective. It did not create the blasts of hot air associated with a wood stove or forced air furnace. Instead, it warmed the walls, the floor, the furniture, and the people in the room through direct infrared radiation. This type of heat is often described as more comfortable than convective heat, because it warms objects and bodies without drying the air or creating drafts. A room heated by a Pechka felt warm even when the air temperature was relatively cool. The Pechka was also multifunctional. The top surface of the stove was used for cooking, particularly for slow-simmered dishes like stews and porridges that benefited from long, gentle heat. Recesses built into the side of the stove could hold pots of water, keeping them warm for washing or drinking. In some designs, a wide platform was built on top of the stove, large enough for a person to sleep on. This sleeping platform, called a leżanka, was the warmest place in the cabin, and it was often reserved for the elderly or the sick. The efficiency of the Pechka was remarkable. Studies of traditional Russian stoves have measured combustion efficiencies of 85 to 95%, far higher than the 50 to 60% typical of an open fireplace. This meant that nearly all the energy in the wood was captured and used to heat the home rather than being lost up the chimney. In practical terms, a family using a Pechka might burn half as much wood as a family using an open fireplace to heat the same space. Over the course of a winter, this difference could mean the difference between having enough fuel to last and running out in February. The Pechka was not common in North America, though similar designs were occasionally built by Scandinavian and Eastern European immigrants. The more typical heating system in American log cabins was the open fireplace, or, later, the cast iron stove. These systems were simpler to build and required less skill, but they were also less efficient. The open fireplace in particular was notorious for drawing more heat up the chimney than it radiated into the room. But in regions where wood was abundant and labor was scarce, simplicity often won out over efficiency. The Pechka represents the extreme end of the thermal mass heating system, a device that turned a log cabin into a space that could be heated once a day and remained comfortable through the night and into the next afternoon. It was not practical in all contexts, but where fuel was limited and winters were severe, it was an elegant solution to the problem of staying warm. The stove was the fire. The fire was the stove, and the two together created a warmth that was steady, reliable, and sufficient. But even without a Pechka, every cabin required a ritual for managing the fire through the night. The fire could not burn continuously without consuming fuel at an unsustainable rate. It had to be reduced, controlled, and preserved in a way that allowed it to be rekindled easily in the morning. This practice was called banking the fire, and it was as essential as building the walls or sealing the joints. The preservation of fire overnight was a skill that required knowledge, attention, and discipline. A fire that burned freely through the night would consume wood at a rate that few families could sustain. A fire that went out completely meant starting over in the morning with flint and steel, or walking to a neighbor's cabin to borrow coals, a humiliating admission of poor fire management. The solution was to bank the fire, reducing it to a slow smolder that produced just enough heat to keep the cabin from freezing, while preserving a core of live embers that could be coaxed back to flame at dawn. Banking began in the evening, after the final meal had been cooked and the cabin was ready for sleep. The process started with the reduction of the fire. If the hearth still contained large logs, they were allowed to burn down until only coals and small fragments remained. New wood was not added. The goal was to create a bed of hot coals, not flames, that could be managed and controlled. Once the fire had reduced to coals, the next step was to consolidate them. Using a poker or a flat shovel, the person tending the fire would rake the coals into a tight pile at the back or center of the firebox. The pile had to be compact. Spreading the coals out would expose more surface area to the air, causing them to burn faster. A tight pile reduced the surface area and concentrated the heat, slowing the rate of combustion. The critical step was the application of ash. Fine wood ash taken from the edges of the firebox or from a previous fire was shoveled or sprinkled over the pile of coals. The layer of ash had to be thick enough to restrict airflow, but not so thick that it smothered the coals entirely. Typically, a layer of 1 to 2 inches was sufficient. The ash acted as an insulator, trapping the heat within the coals and preventing oxygen from reaching them in large quantities. With the airflow reduced, the coals entered a state of very slow combustion. They were still burning, but at a much lower rate. The surface of the coal pile might glow faintly through the ash, or it might appear completely dormant. The temperature within the pile remained high, hot enough to ignite fresh wood instantly, but the rate of fuel consumption dropped to a fraction of what it had been during active burning. A properly banked fire could hold for 8 to 12 hours, depending on the size of the coal bed and the quality of the ash cover. The skill in banking was knowing how much ash to apply. Too little, and the coals burned through before morning. Too much, and the coals were extinguished, leaving only cold ash to greet the person tasked with restarting the fire. This knowledge came from experience. A child learning to bank a fire might err on one side or the other several times before developing the judgment to get it right consistently. But once learned, the skill became second nature, executed without conscious thought at the end of each day. The choice of wood also affected the success of banking. Hardwood coals, oak, maple, hickory, lasted longer than softwood coals because they were denser and contained more carbon. A bed of hardwood coals could be banked and expected to last through the night with a reasonable margin of safety. Softwood coals from pine or spruce burned more quickly and were more likely to fail before morning. For this reason, families in regions with access to mixed forests often saved their hardwood for the evening fire, using softwood during the day when the fire could be tended more frequently. In the morning, the process was reversed. The person waking first, often the eldest daughter or the wife, would approach the hearth and carefully rake away the layer of ash. Beneath it, if the banking had been successful, the coals would still be glowing. Fresh kindling, thin splits of dry wood, bark, or wood shavings, was added to the coals. Within seconds, the kindling would catch and flames would appear. Larger pieces of wood were added and the fire was rebuilt for the day. If the banking had failed and the coals were dead, the morning was much harder. Restarting a fire from scratch required flint and steel or a fire drill or a trip to a neighbor's home to borrow coals. All of these options were time-consuming and, in the case of visiting a neighbor, socially awkward. A household that consistently let its fire die was seen as poorly managed. Fire was a shared resource in isolated communities, and neighbors would help in an emergency, but repeated requests for coals suggested neglect or incompetence. The consequences of a failed fire went beyond inconvenience. In deep winter, a cabin without a fire could become dangerously cold within hours. Water froze. The stored heat in the log walls dissipated. Children woke to frost on the bedding. The family's survival depended on the fire, and the fire depended on the discipline and skill of the person who banked it each night. This responsibility was not taken lightly. The ritual of banking also had a psychological dimension. It marked the transition from day to night, from activity to rest. The act of covering the coals was a form of trust. Trust that the fire would last. Trust that the cabin would remain warm. Trust that morning would come and the cycle would continue. In a harsh and uncertain environment, this trust was not trivial. The fire was life. To bank it was to acknowledge the limits of human endurance and to place faith in the materials and techniques that had been proven over generations. But fire alone was not enough to keep a cabin warm. The environment outside the walls could be harnessed as well in ways that seemed counterintuitive. Snow, frozen water, could become insulation. The very substance that represented the cold could be turned into a tool for preserving warmth. This practice, snowbanking, was common in the coldest regions and added another layer to the cabin's thermal defenses. Snow is mostly air. When it falls and accumulates, the individual crystals create a loose, porous structure in which air is trapped in countless tiny pockets. This trapped air is what makes snow an effective insulator. Air does not conduct heat well, and when it is immobilized within a solid matrix, it resists heat transfer even more effectively. A layer of snow can have an insulating value comparable to fiberglass or foam, depending on its density and moisture content. Settlers in the northern forests understood this. They observed that animals, mice, voles, rabbits, burrowed into snow to escape the cold. They noticed that the ground beneath a deep snowpack remained unfrozen even when the air temperature dropped far below zero. And they realized that this same principle could be applied to their homes. By piling snow against the exterior walls of the cabin, they could create a secondary thermal barrier that reduced heat loss and protected the logs from the drying effects of cold wind. The practice of snowbanking began in late autumn or early winter, as soon as enough snow had accumulated. The process was simple but labor-intensive. Using shovels or wooden boards, snow was scooped from the surrounding area and piled against the walls of the cabin. The pile had to be built carefully, sloping away from the wall at the base to prevent the weight from pushing inward and extending upward as high as practical, often 6, 7, or even 8 feet. The snow was not packed tightly. It was left relatively loose, which maximized the air content and therefore the insulating value. Packed snow, while more stable, conducted heat more readily because the air pockets were compressed. The goal was not to build a snow fort, but to create a fluffy, airy barrier that would resist heat transfer while remaining in place through the winter. The effectiveness of snowbanking was immediate and measurable. On nights when the air temperature dropped to 20 or 30 degrees below zero, the exterior surface of a log wall without snowbanking might fall to near the ambient temperature. The temperature gradient across the log would be steep and heat would be drawn from the interior at a high rate. With snowbanking, the exterior surface of the log was insulated from the coldest air. The snow maintained a temperature of approximately 32 degrees Fahrenheit, the freezing point of water, against the log's surface, regardless of how cold the air became. This reduced the temperature gradient across the log, slowing the rate of heat loss and allowing the thermal mass of the wall to function more effectively. The layer of snow also blocked wind. Wind increases the rate of heat loss through a process called convective cooling. Moving air strips heat from a surface much more efficiently than still air. A cabin wall exposed to a strong wind loses heat rapidly, even if the wall is well insulated. Snowbanking eliminated this wind exposure, creating a still air layer between the snow and the log that further reduced heat transfer. There were challenges to snowbanking. The primary concern was moisture. Snow in contact with the logs could melt if the interior of the cabin was very warm, particularly during the day when the fire was burning actively. This meltwater could soak into the wood, promoting rot at the base of the wall. To prevent this, some families built a straw or hay barrier between the wall and the snow. Posts were driven into the ground several feet from the cabin, and the space between the posts and the wall was filled with dry straw. The straw created an insulating layer that kept the snow from direct contact with the logs, while also providing additional insulation. Another concern was the weight of the snow. Wet, heavy snow could exert significant pressure against the walls, particularly if it was piled too steeply or allowed to accumulate to excessive heights. Proper sloping and periodic inspection helped to manage this risk. If the snow began to slump or press too heavily, it was removed or reshaped. Despite these challenges, snowbanking was widely practiced in regions where winter was long and severe. It was a free resource requiring only labor to apply, and it provided a substantial benefit in terms of reduced fuel consumption. A cabin with snowbanking could be kept warm with less wood, which meant fewer trips into the forest to cut and haul timber, and a greater chance that the wood supply would last through the entire winter. The use of snow as insulation also extended to other structures. Root cellars, which were used to store vegetables and preserve foods, were often covered with snow to maintain a stable temperature just above freezing. Animal shelters were banked with snow to protect livestock from the worst of the cold. Even temporary camps and hunting shelters benefited from snow walls, which could be built quickly and provided immediate relief from wind and cold. The principle at work, that cold material can insulate against colder air, was not unique to snow. Soil, when frozen, also provided insulation. Cabins built partially underground, with earth bermed against the walls, benefited from the stable temperature of the soil, which remained warmer than the air even in the depths of winter. This technique was common in sod houses and dugouts on the treeless plains, where logs were not available, but earth was abundant. Snowbanking, then, was not a desperate measure. It was a calculated use of available resources to enhance the thermal performance of the cabin. It required foresight, labor, and maintenance, but it delivered tangible results. The cabin stayed warmer, the wood lasted longer, and the family had a better chance of making it to spring without exhausting their fuel supply or their physical reserves. But the cabin's defense against the cold did not end with the walls and the snow. Inside, another layer of protection was needed, one that operated at the scale of the individual body rather than the building. The final buffer against the cold was the bed itself and the materials that surrounded the sleeper through the long hours of the night. The warmth of the cabin ended at the edge of the bedding. Beyond that boundary, the cold of the room, however moderated by fire and thermal mass, still sought entry. The bed was the final defense, a microclimate constructed from layers of fabric, fill, and shared body heat. In a cabin where nighttime temperatures could drop to the 40s or 50s, the bed had to function as a portable furnace, trapping the heat generated by sleeping bodies and preventing its escape into the surrounding air. The foundation of the bed was the tick. This was a large bag, typically made of coarse linen or cotton ticking, stuffed with whatever material was available and appropriate to the season. In frontier cabins, the most common fill was straw or dried corn husks. These materials were abundant, free, and easily replaced. A straw tick was firm and rustled loudly with any movement, but it provided critical insulation from below. The floor of a cabin, even in a room with a fire, remained the coldest surface. Cold air, being denser than warm air, settled at floor level, and without insulation between the sleeper and the floor, body heat would be drawn away through conduction. A straw tick, 6 or 8 inches thick, created a barrier of trapped air between the sleeper and the floor. The hollow stems of the straw formed thousands of tiny channels that resisted heat transfer. Over time, the straw compressed under the weight of the sleepers, reducing its effectiveness, and it had to be emptied and refilled periodically. But when fresh and properly filled, a straw tick was sufficient to prevent the numbing cold that came from sleeping on bare boards or packed earth. Wealthier families, or those with access to waterfowl, used feather ticks. Goose or duck feathers provided superior insulation because they were lighter and more compressible than straw, and they retained their loft better over time. A feather tick was a luxury, often passed down through generations and considered a valuable part of a household's goods. The feathers trapped air in the spaces between their barbs, creating an insulating layer that was both warm and soft. A feather tick also dried more quickly than straw if it became damp, an important consideration in a cabin where condensation and humidity were constant concerns. Above the tick, the sleeper was covered with blankets and quilts. These layers were not interchangeable. Blankets, typically made of wool, provided warmth through their density and their ability to trap air within the fibers. Wool remained warm even when damp, a property that made it invaluable in the humid environment of a cabin heated by fire and occupied by breathing, sweating bodies. A single wool blanket might weigh several pounds and provide warmth equivalent to 2 or 3 cotton blankets. Quilts served a different function. They were lighter than blankets, but often more effective at trapping heat because of their construction. A quilt consisted of 3 layers: a top fabric, a middle layer of batting, and a backing fabric, stitched together in a pattern that created pockets. These pockets held the batting in place and prevented it from shifting or clumping. The batting, often made of wool, cotton, or scraps of old fabric, provided the insulating layer. The stitching created a series of small air chambers that resisted heat loss while allowing the quilt to drape and conform to the shape of the sleeper. The log cabin quilt pattern, common in the 19th century, was more than decorative. It was symbolic. The central square of the quilt, often made of red fabric, represented the hearth. The surrounding strips of light and dark fabric, arranged in a stepped pattern, represented the logs of the cabin walls and the play of firelight and shadow across them. A log cabin quilt was a map of the home itself, a textile representation of the structure that protected the family. It was also heavy, made from substantial fabrics, and provided real warmth in addition to its symbolic significance. The number of layers varied by temperature and availability. On the coldest nights, a family might sleep under 3 or 4 quilts, each adding to the total insulating value. The weight of the bedding was itself a source of comfort. Heavy blankets and quilts pressed down on the body, reducing air circulation around the sleeper and creating a sealed environment where body heat accumulated. This weight also had a psychological effect, a sense of being held and protected that made the cold outside the bed more bearable. Before entering the bed, the bedding was often pre-warmed. This was done with a bed warmer, a metal pan with a long handle, filled with hot coals from the fire. The pan was slid between the sheets and moved back and forth to warm the fabric. The coals were contained within the pan, so there was no risk of fire, but the radiant heat from the metal was enough to take the chill off the linens. A bed warmed in this way was a small luxury, a few minutes of comfort that made the transition from the fireside to the cold sheets less brutal. In households without a bed warmer, other methods were used. Heated stones wrapped in cloth were placed at the foot of the bed. Bottles filled with hot water, if glass or ceramic bottles were available, served the same purpose. These warmers did not last through the night, but they provided enough heat to allow the sleeper to fall asleep before the cold fully set in. Once asleep, the body's own heat, trapped by the layers of bedding, was sufficient to maintain warmth. Shared body heat was another critical component. In large families, children slept 2, 3, or 4 to a bed. This was not only a matter of space, but of survival. Each additional body in the bed contributed heat, and the combined output of multiple sleepers could raise the temperature within the bedding by 10 or 15 degrees. The bodies pressed together, minimizing the surface area exposed to the cold air, and the shared warmth created a pocket of comfort that a single sleeper could not achieve alone. Adults often slept in pairs for the same reason. A married couple in a shared bed benefited from the warmth of two bodies, and the combined heat was enough to make a cold room tolerable. In cabins where space allowed, children might sleep in the loft while parents slept on the ground floor. But even then, the principle remained. Warmth was shared, not individual. Clothing worn to bed also mattered. In the coldest weather, people did not undress for sleep. They wore wool stockings, flannel nightshirts, and knit caps. The cap was particularly important, as a significant amount of body heat is lost through the head. A wool cap pulled down over the ears could make the difference between a restless, shivering night and one of tolerable sleep. The nightshirt provided a layer of insulation over the torso, and the stockings protected the feet, which, being farthest from the heart, were most vulnerable to cold. The bed, then, was not a piece of furniture. It was a system, carefully designed to trap and hold heat in an environment where heat was scarce. The tick insulated from below. The blankets and quilts insulated from above. The clothing insulated the body directly, and the shared warmth of multiple sleepers multiplied the effectiveness of all the other layers. Together, these elements created a microclimate warm enough for sleep, even when the room beyond the bedding hovered near freezing. But this system required resources: fabric, feathers, straw, wool, and the labor to maintain it. Bedding had to be aired regularly to prevent mold and to restore its loft. Ticks had to be refilled. Quilts had to be mended. The effort was constant, but it was essential. Without warm bedding, the warmth of the cabin was incomplete. The fire could heat the room, the walls could store that heat, but if the bed failed, the night would be unbearable. The experience of sleeping in such conditions and waking to tend the fire was documented by those who lived it. Their accounts reveal the gap between the idealized image of the log cabin and the lived reality of frontier survival. The written record of winter in the log cabin is sparse, but where it exists, it reveals a reality far removed from the romanticized image of the pioneer hearth. The cold was not always held at bay. The fire did not always burn true, and the labor required to maintain warmth was exhausting, repetitive, and often barely sufficient. Susanna Moodie, an English gentlewoman who emigrated to the Canadian backwoods in the 1830s, left one of the most detailed accounts of winter survival in a frontier cabin. Her book, Roughing It in the Bush, describes mornings when the cold was so intense that everything liquid in the cabin froze solid overnight. Water left in a bucket by the hearth formed a solid block of ice. Ink froze in its bottle. Bread, if it had been baked the previous day and left, to cool, became rock hard and had to be thawed by the fire before it could be eaten. Moody's cabin was not well constructed by the standards of experienced builders. The logs were green, meaning they had not been properly seasoned before use. Green wood contains a high percentage of water, and as it dries, it shrinks. The shrinkage opened gaps between the logs, and the chinking, hastily applied by laborers who were paid by the cabin rather than by the quality of the work, fell out or cracked within the first winter. Cold air poured through the gaps, and no amount of additional daubing seemed to seal them permanently. The wood provided for the fire was also green. It hissed and steamed when placed on the flames, releasing moisture in clouds of smoke that filled the cabin before finding its way out through the chimney. Green wood does not burn hot. Much of the fire's energy is consumed in evaporating the water within the wood, and what remains produces a weak, smoky flame that provides little heat. Moody describes the frustration of standing by the hearth, shivering, while the fire sputtered and refused to catch properly. The children cried from the cold. The adults worked in silence, their hands numb, their breath visible in the air. This struggle with inadequate materials and poor construction was common among new settlers. Those who arrived in late autumn or winter often had no choice but to build quickly and move in before the structure was properly finished. The gaps would be sealed later, when time allowed. The wood would be replaced with seasoned timber in the spring. But in the meantime, the family endured. They burned more wood than they should have needed, and they woke each morning to frost on the interior walls and ice in the water pail. Yet even in these difficult conditions, there were moments of stillness and comfort. Catherine Parr Trail, Susanna Moody's sister, also emigrated to Canada and wrote about her experience in the backwoods of Canada. Trail's accounts are less bitter than Moody's, and they capture the quiet pleasures that could be found in a well-managed cabin on a winter evening. She describes the firelight playing across the darkened rafters, casting shadows that shifted and danced with the movement of the flames. The fire, when it burned well, produced a glow that was both warm and hypnotic. The gray of the ash mixed with the gold of the flame, and the interplay of the two colors created a visual rhythm that held the attention. There was a meditative quality to watching the fire, a way of losing oneself in the slow transformation of wood into light and heat. The scent of the fire was also a source of comfort. Burning pine released a resinous smell, sharp and clean, that filled the cabin and seemed to coat the throat with each breath. Ash, when stirred, carried a faint alkaline bitterness. The combination of the two created an atmosphere that was distinctly domestic, a smell that meant warmth and safety. For those who had grown up in cities or towns, the scent was foreign at first, but it quickly became associated with home. Trail also notes the silence of the winter forest. Once the fire was banked and the cabin settled into the quiet of the night, the only sounds were the occasional creak of the logs, adjusting to the temperature change, and the faint whisper of the wind in the trees outside. The snow absorbed sound, muffling the world beyond the walls. Inside, the stillness was almost complete. It was a silence that could be oppressive for those accustomed to the noise of society, but it could also be restful, a kind of enforced peace that allowed for thought and reflection. The psychological toll of winter isolation was real. Families spent months confined to a single room, seeing no one outside their immediate household. Tensions rose. Small annoyances became major grievances. Children, unable to play outside for long periods, grew restless and quarrelsome. Adults, burdened with the constant labor of maintaining the fire, cooking, and managing the household, found little time for rest or leisure. But there was also a rhythm to the days that provided structure. The fire had to be tended at regular intervals. Meals had to be prepared. Snow had to be melted for water. Clothing had to be mended. These tasks, though repetitive, created a pattern that held the household together. The rhythm was not chosen, it was imposed by the needs of survival. But it became familiar, and in its familiarity, it was bearable. The contrast between struggle and stillness defined the experience of winter in the log cabin. There were days when the cold seemed insurmountable, when the fire refused to burn, when the wind found every gap in the chinking and filled the room with icy drafts. And there were evenings when the fire burned true, when the walls radiated steady warmth, when the family gathered in the glow of the hearth and felt, for a few hours, that they had achieved something close to comfort. This duality was not a failure of the cabin or the heating system. It was the nature of living in a place where winter was harsh and resources were limited. The cabin could not eliminate the cold. It could only moderate it, turning the lethal into the tolerable, and the tolerable into the occasionally pleasant. For those who survived, the memory of winter was not one of unbroken hardship, but of hardship punctuated by moments of warmth and light. The fire itself and the smoke it produced was not merely a functional necessity. It carried meaning beyond its physical properties, becoming a symbol and a guardian in the minds of those who depended on it. Smoke was a constant presence in the log cabin. It filled the room before escaping through the chimney or the gaps in the roof. It stung the eyes and irritated the lungs. It coated every surface with a fine, dark residue. But it was also more than a byproduct of combustion. It was a preservative, a disinfectant, and in the minds of many settlers, a protective force that stood between the household and the dangers of the cold, the darkness, and the wilderness beyond. The earliest log structures in Scandinavia and Russia were built without chimneys. The smoke from the central hearth rose into the interior, filling the upper portions of the room, before finding its way out through small vents in the roof or gaps between the logs. These buildings were called smokehouses, and they represented an intentional design choice rather than a primitive oversight. The smoke served multiple functions, and the discomfort it caused was accepted as the price of those benefits. Smoke preserved the wood. The compounds in wood smoke, primarily creosote and phenols, are toxic to fungi, bacteria, and insects. When smoke filled the interior of a cabin, It coated the logs, the rafters, and any stored food with a thin layer of these compounds. This coating prevented rot, discouraged insect infestation, and extended the life of the structure. Cabins that had been continuously inhabited and heated for decades developed a hard, black surface on the interior logs, a layer of concentrated smoke residue that was nearly impervious to decay. Smoke also preserved food. Meat, fish, and sausages hung from the rafters were exposed to the smoke continuously, which dried them and imparted the preservative compounds. This method of preservation was essential in a time before refrigeration, and it transformed the cabin into a functional smokehouse. The same fire that heated the living space also processed the food supply, making the cabin a dual-purpose structure. The disinfectant properties of smoke were also valued. In a time when disease was poorly understood and often fatal, any measure that reduced illness was considered worth the discomfort. Smoke was believed to purify the air, and to some extent, this belief was justified. The compounds in smoke do kill airborne bacteria, and the fire and the dryness it created were inhospitable to many pathogens. Whether the benefit outweighed the harm caused by chronic smoke inhalation is debatable, but for settlers who had few other options, the smoke was seen as a net positive. Beyond its practical function, smoke took on a symbolic role. It was the visible manifestation of the fire, the proof that the hearth was active and the home was warm. A column of smoke rising from the chimney could be seen from a distance, signaling to neighbors that the household was alive and functioning. In isolated communities, the presence or absence of smoke was a way of checking on distant families. If a chimney remained smokeless for more than a day or two in winter, it was cause for concern, and someone would make the journey to investigate. Within the cabin, the smoke was sometimes referred to as the guardian, or the spirit of the fire. This language was not literal. Most settlers were practical people with little time for superstition, but it reflected an acknowledgement that the smoke represented something more than just a nuisance. It was the evidence of the fire's work, the sign that the cold was being held at bay. To see smoke curling through the rafters was to know that the fire had not failed, that warmth was present, and that the night could be endured. The soot that accumulated on the rafters and walls was not cleaned away. It was allowed to build layer upon layer, creating a visual record of the fires that had burned in the cabin. Each streak of black, each patch of darkened wood told the story of a winter survived, a family kept warm, a fire that had done its work. The soot was not decorative, but it was meaningful. It was a material document written in carbon and tar of the household's endurance. In some cabins, the soot was so thick that it could be scraped off in chunks. This soot was sometimes collected and used as a fertilizer or as a pigment for making ink, but most often it was left in place, a reminder of the work that had been done and the work that would need to be done again when the next winter came. The smell of smoke was also part of the cabin's identity. It permeated the fabric, the bedding, the clothing. It clung to hair and skin. For those who lived in the cabin, the smell became unnoticeable, a part of the sensory background that was simply the way things were. But to a visitor entering the cabin from the cold, the smell was strong and immediate, a mix of wood smoke, ash, and the faint creosote tang of old soot. This smell, for many settlers, became the smell of home. It was the scent that greeted them when they returned from the forest or the field. It was the smell that filled the cabin on winter evenings when the fire burnt bright. And it was the smell that lingered in their memory long after they had left the cabin for a different kind of dwelling. In letters and memoirs, former frontier residents often mentioned the smell of smoke with a kind of nostalgia, as though it represented not just a physical reality, but a time and a way of life that had been left behind. The acceptance of smoke as a guardian was not universal. Those who came from urban backgrounds, or who had been raised in homes with proper chimneys and well-ventilated rooms, found the smoke unbearable. Susanna Moody, in her account, describes the smoke as one of the worst aspects of cabin life, a constant irritant that made her eyes water and her lungs burn. She did not see it as a guardian. She saw it as a failure of design, a problem to be solved rather than endured. But for those who had grown up in smoky cabins, or who had learned to live in them over time, the smoke was simply part of the system. It was the price of warmth. It was the byproduct of survival. And it was, in a strange way, a companion. A presence that filled the space, marked the passage of time, and reminded the inhabitants that they were not alone in the struggle against the cold. The soot on the rafters was memory made visible. The smoke in the air was the fire's breath, and together they created an atmosphere that was as much psychological as physical, a sense that the cabin was not just a structure, but a living thing, maintained through effort and inhabited through will. This understanding of the cabin as a living system, rather than a static object, was central to its effectiveness. The structure required care, attention, and knowledge, and that knowledge, passed down through observation and practice, was what made survival possible. The builders of log cabins did not work from blueprints. They did not calculate R values or thermal conductivity coefficients. They did not measure heat loss in BTUS or model airflow with computer simulations. Yet the cabins they built performed well, often better than structures designed with the benefit of modern science. This was because the knowledge embedded in the walls was empirical, accumulated over generations, and tested against the only standard that mattered: survival. A builder learned by watching. He observed which cabins stayed warm and which did not. He noted the techniques used by those whose families thrived through the winter and avoided the mistakes of those who struggled. This knowledge was not written down. It was demonstrated, practiced, and refined with each structure built. Over time, patterns emerged, rules of thumb that could be applied without needing to understand the underlying physics. One such rule was the preference for cedar over pine, and pine over spruce. A builder might not have known that cedar's closed-cell structure resisted moisture absorption and minimized checking, but he knew that cedar logs stayed tight and did not crack as badly as pine. He knew that a cabin built from cedar required less maintenance and fewer repairs over the years. This knowledge was practical and immediate. It did not require an explanation. It only required observation and memory. Another rule concerned the orientation of the logs. A builder learned to place the butt end of one log facing one direction and the butt end of the next log facing the opposite direction. This alternated the natural taper of the logs and created a more level wall. It also distributed the gaps more evenly, making the chinking easier to apply. A novice might stack all the logs with the butts facing the same way, creating a wall that leaned and had irregular gaps. An experienced builder knew better, not because he had studied geometry, but because he had seen the consequences of poor stacking. The height of the ceiling was another area where empirical knowledge governed design. A cabin with a 7-foot ceiling felt warmer than one with an 8-foot ceiling, even though the difference was only 12 inches. This was true regardless of the type of wood used or the quality of the chinking. The reason: that warm air rises and that a lower ceiling kept that warmth closer to the living space was understood intuitively. A builder did not need to invoke the concept of convection. He only needed to have spent a winter in both types of rooms and to have noted the difference. The practice of hewing logs flat was another piece of embedded wisdom. Hewing was hard work, and a builder who skipped this step saved time and effort. But the resulting cabin was colder, draftier, and required more fuel to heat. A builder who had experienced both hewn and unhewn cabins would choose to hew, even though it doubled the labor of construction. The knowledge that flat surfaces created tighter seals was not theoretical. It was felt in the body, in the warmth or cold of the room. And that feeling was a more powerful teacher than any diagram or formula. The use of lime in the Daubing mixture was another example. Lime-based mortar lasted longer than clay alone and allowed the wood to breathe, preventing rot. A builder might not have understood the chemistry of lime carbonation or the concept of vapor, permeability, but he knew that lime mortar did not crack as easily as clay, and that the logs beneath it stayed dry and sound. This knowledge was transmitted from one builder to the next, often without any explanation of why lime was superior. It was simply the way it was done, and those who ignored the practice paid the price in repairs and rot. The placement of the hearth was also guided by experience. A hearth on an exterior wall lost more heat than one on an interior wall. A hearth in the center of the room radiated heat in all directions. These principles were not derived from theory. They were observed in the buildings that worked and the buildings that did not. A builder learned to place the hearth where it would do the most good, and he learned to size the firebox appropriately for the volume of the room. A firebox that was too large consumed too much wood. A firebox that was too small could not heat the space adequately. The correct size was a matter of proportion, learned through trial and error. The practice of banking the fire was also learned knowledge. A child growing up in a log cabin watched the adults cover the coals each night and learned the technique by imitation. The child might be allowed to try under supervision and would quickly discover whether too much or too little ash had been applied. The feedback was immediate. Either the coals lasted through the night or they did not. There was no abstract theory to learn. There was only the practical skill of managing fire, a skill that became second nature with repetition. This accumulated knowledge was resilient because it was distributed. No single person held all the information. Instead, each builder, each family, each community contributed to the collective understanding of how to build and maintain a warm cabin. When a new technique was discovered, perhaps a better way to seal a corner joint or a more effective mixture for daubing, it spread through observation and imitation. Those who adopted the improvement benefited. Those who did not were left behind. This process of knowledge transfer was slow but effective. It did not produce rapid innovation, but it did produce reliability. A cabin built using traditional methods and materials was likely to perform well because those methods had been tested over hundreds or thousands of winters. The design was conservative, but it was proven. And in a context where failure meant death, conservatism was a virtue. Modern science has since confirmed much of what traditional builders knew intuitively. Studies of thermal mass, insulation, and air sealing have provided explanations for why log cabins work as well as they do. But the builders did not need these explanations. They needed only to observe, remember, and apply what they had learned. The wisdom was embedded in the act of building itself, in the choices made about materials, dimensions, and techniques. It was wisdom that did not require literacy or formal education. It required only attention, practice, and the willingness to learn from experience. This pragmatic approach extended to every aspect of cabin life. The fire was managed not according to a schedule, but according to need and observation. The chinking was repaired when gaps appeared, not on a fixed calendar. The bedding was adjusted based on the temperature of the night. The system was flexible, responsive, and human-scaled. It worked because it was designed by people who lived in it and who could feel immediately whether it was working or not. The knowledge embedded in the walls was not romantic. It was not poetic. It was practical, hard-won, and essential. And it was this knowledge, more than any single technology or material, that made the log cabin a viable form of shelter in the harshest climates on Earth. But the cabin was not just a collection of techniques and materials. It was a system in which every element worked together, each supporting the others in a web of interdependence that created warmth from wood, fire, and time.